Welcome to the Walton Pi. Today we're going to be talking about elementary families of sets. So to start off, an elementary family is just any subset of a power set, so the collection of all subsets of X, such that, first off, the empty set is in our elementary family. Two, if we have two elements, E and F, already in our elementary family, then their intersection is also going to be in that collection E. And then if we have a set E in our elementary family, that implies that the complement of E is going to be a finite pairwise disjoint union of elements in E. So we're able to construct it by taking finitely many things from our elementary family, unioning them together, and none of those things had any overlap. Okay, so it's not telling us that X itself or the complement itself is in our elementary family, just that we can create it using a finite union of things. So let's talk about a couple properties that elementary families have. So if E is an elementary family, then the set of all finite unions of pairwise disjoint elements of E is going to be an algebra. Okay, so let's go through and prove that. So let's let A be the set of all pairwise disjoint finite unions of elements of E. So the thing that we think is going to be an algebra, we're going to now show that this is in fact an algebra. So to see it's an algebra, we're going to verify 4 claims. First, if A is in our algebra, or in our proposed algebra, and F is in our elementary family, then A minus F, or the set difference, is going to be in our collection A. 2, if A and B are in our collection A, then A minus B is going to be an A. The whole set X is going to be an element of A, and for any elements we pick, A and B, their union is also going to be an A. If we verify these 4 claims, these are the 4 properties of algebras that we need, and so these are going to be enough to be able to conclude that it is in fact an algebra. So first claim, let's go through and do that proof. So let's start by just picking A1 through AN in our elementary family, and A is going to be a finite disjoint union of those AIs. That's what it means for something to be in our potential algebra, and so we go through and just say, okay, we have that element A, what are the pieces that make it up? So since E is an elementary family and F is an element of that elementary family, we can write the complement of F as a finite disjoint union of EIs, where those EIs come from our elementary family. So then that tells us that A minus F is the same as A intersected with X minus F. So then we can be able to write that as a union of AIs intersected a union of EJs, which if you do some De Morgan law properties or a lot of set following like element chasing, you're able to write this as the union from I equals 1 to n, unioned with the elements j equals 1 to k of the AIs intersect EJs. Each of those are elements of our elementary family, which tells us that we have constructed A minus F as a pairwise disjoint union of elements of E. Therefore, if A is in our potential algebra and F is in our elementary family, A minus F is an element of A. Claim 2. If A and B are in our potential algebra, then A minus B is in our algebra. Now this is very similar to the previous one. The previous one was where we were subtracting something off in our elementary family. This is now subtracting off something that is in our potential algebra. So we're going to be using the previous property, and we're going to go through and do this very carefully. So because B is in our algebra, we can find B1s through Bn's, where each of those are pairwise disjoint with each other, and we can be able to write B as the finite disjoint union of those BIs. Then we're able to say A minus B is A minus the union of those BIs, which is the intersection of the A minus BIs. By claim 1, each of the A minus BIs is in our algebra, so we are able to write A minus BI as a union of elements from our elementary family, which we're going to call Wij's. And so then A minus B is going to be the intersection of all of these, and so then we are able to write that as a union of Wij J1s intersected the W2J2s, and so on, we're able to write all of these, where theWij's are all in our elementary family, and theWij's intersected with Wik's is empty for every j not equal to k. Which then concludes our thing, because we've been able to write a minus b as this union of elements in our elementary family, and so we are going to be able to then in fact say that a minus b is going to be in our proposed algebra. Claim 3, x is in our algebra. Since the empty set is in our elementary family, by the definition of an elementary family, x is the same as x minus the empty set, must be a pairwise disjoint union of elements of our elementary family, and is therefore going to be in our algebra. And claim 4, if we have a and b in our algebra, a union b is going to be in our algebra. So let's let a and b be in A. By claims 2 and 3, x minus a is going to also be in A. Note that we can be able to write a union b as a take out b union b. That's then a pairwise disjoint union of elements in A, each of which can be written as pairwise disjoint unions of elements in E. So that tells us that a union b is going to be in our algebra A. So we have successfully shown that if E is an elementary family, then the set of finite unions of pairwise disjoint elements of E is going to be an algebra. Thank you so much for watching. I hope this video was helpful. If it was, please like and subscribe. It really helps me to keep making these videos. And if there's other things you'd like me to make a video about, please leave that in the comment section down below. Have a great day, and good luck with all of your math.